Hello. Okay, section 4.4, recursive algorithms. So this is very interesting. This is how we can use programming, I guess, the way I think of this, to sort of mimic inductive sort of proofs and inductive reasoning that we've had in the past. So let's go through some examples here. So we know what this n factorial is. You multiply the first n numbers together and you get n factorial. So here's a here's an algorithm for computing n factorial, and then we'll see if it works. It says it's a recursive algorithm, right, to compute n factorial. So you input n, an integer greater than or equal to 0, and the output is going to be n factorial. So the function is factorial n, and what happens is if n equals 0, you return 1. And then, then you return n times factorial n minus of n minus 1. So notice how what's happening here is that to calculate n factorial, we need to have knowledge of the factorial of n minus 1. But you see, if you run this program, it would eventually end up where n minus 1 is 1, right? And then so what happens is then then when when the input is 2, it would calculate as 2. So it basically generates the answer. So here's the proof that it works, right? So the basic step is that we have already observed that if n is equal to 0, algorithm 2 or 4.4.2 correctly returns the value of 0 factorial of 1. So it's done for the first step. So the inductive step, right? Let's assume that this algorithm, right, correctly returns the value of n minus 1 factorial. Okay, that's our inductive hypothesis, right? Then if n is greater than 0, now suppose that n is input into this algorithm. Well, since n is not equal to 0, right, when we execute the function in the algorithm, what happens? We proceed to line 4, right, and it says, line 4, at line 4, it says compute the value of n minus 1 factorial. Well, it's already, by our assumption, we have that is accurate, right? So at line 4, the function correctly computes the value n minus 1 factorial times n, which is n factorial. Therefore, this algorithm correctly returns the value of n factorial for every integer n greater than 0. So you kind of get your head around how that's happening. Let's look at another example here. So this is something that is really kind of interesting. There was an exercise that we did. I did not go through the details about triminoids or whatever. Yes, okay. What are they? The little L-shaped figures. Let me just quickly go through the proof, and then we'll see what's happening. So essentially what you have is this algorithm correctly constructs a tiling by what is it? Trimonians. What are the triminoids? Okay, of an n by n deficient board where n is a power of 2. Now, what a deficient board is, there's like one square missing. Okay, and then what these triminoids are basically L-shaped things. Here, let's go quickly to that so you can see what we're dealing with here. So here we go. So if you look at this, this is something that was in chapter 2 that I didn't make a big deal of, but it's really quite interesting. So this is what they look like. They're just these little L-shaped things. And the tiling problem is that if you have a board, like say this one here, here's an example of a 4x4 board, 1, 2, 3, 4. All right. And it has this square missing. Well, you see you can tile or cover the rest of the board with these little L-shaped things. Okay. And it turns out, if we were to go through this proof, there's a nice inductive proof that this can always be done for any board of size 2 to the n times 2 to the n, okay? And essentially the way you do it is you like this picture kind of illustrates the proof. You assume that you can cover, say, this board, which is a smaller board with triominoes. That's sort of the inductive step. And then what you do is you place this artificial one right here, and then you make believe that these three squares are missing from these three 2 to the k times 2 to the k square boards. And then by the inductive hypothesis, we can basically tile the whole thing. So that's enough to prove that it can be done in general. Okay, so let me get back to chapter 4 where we were. It turns out to implement an algorithm to do that, we simply need to sort of use the idea that this proof exists and use it in the following way, which is very analogous to the way we calculated n factorial. So I'm sorry for this flipping through these things here. I probably should have a more effective way of getting to where I want to be, but that's life. Okay, so here we go. So here it is, 4.4. All right, 4.4. Come on now. Okay, so here it is. Let's look at the proof. So here, watch how it just really mimics the induction, and it simply uses the fact that the induction is correct. So here we go. So this algorithm constructs a tiling by right, I can't even pronounce it, triominoes of n by n deficient board where n is a power of 2. So here it is. The input is just n, and then a power of 2, the board size, right? So that is and then the location L of the missing square, all right? So a tiling of an n by n deficient board, okay, that's the output by these figures. So we're calculating tile NL, okay? So what do we do? So if n equals 2, that's the simple case, then the board is a right triomino T tiled with T, and then you just return it, okay? Okay, so now the next step is divide the board into 4 n over 2 times n over 2 boards. In other words, we're creating 4 smaller boards, right? And we wanted to rotate the board so that the missing square is in the upper left quadrant, okay? Then place one right triomino in the center, right? Just as in that proof that we just went over, as in figure the one I just looked at, 2.45. And then consider each square covered by the center triomino as missing, and denote the missing squares as M1, M2, M3, and M4, okay? So there we have it. Then all we need to do is now apply the tiling command to these smaller subsquares. So we tile n over 2, M1, n over 2, N2, n over 2, N3, n over 2, N4, and that's it. That's the algorithm, and it will spit out the answer. Okay, so there we have it. Here's another one. Let's take a look at robot walking. This algorithm computes the function defined by walk n equals 1 if n equals 1, walk n equals 2 if n equals 2, and walk n equals walk n minus 1 plus walk n minus 2 if n is greater than 2. Now, okay, so let's see how we're going to do this. Well, we input n, right? And the output is going to be walk n, all right? So let's see what we have. So walk n, so if n equals 1 or n equals 2, we just return n, you see, because that's what we want, right? And then we return, right, walk n minus 1 plus walk n minus 2. Now, this, again, almost looks magical, but if you if you just think about it, what does it do? If you run this this program, it will continuously ask itself what to calculate walk n minus 1 is. In other words, it will rerun this program. Eventually, what it will do is we'll go back to the original 1 and 2, right? And then it will start to we'll add 1 and 2 and we'll get 3, right? And then I'll add, then to get the next one, we get, you can see how it sort of falls out. And in fact, it works wonderfully. And this is basically, I guess that's calculating the Fibonacci sequence, right? Yeah, okay. So this is the idea of recursion, where, and here's a good example. We have an idea of that the something is defined in terms of something that has been calculated prior to it, okay? So I don't want to go through this example, but that's the idea, and you'll see there's lots of nice problems in here for you to work on, right? But okay, let's go through this one last where it's a little bit more concrete. It says, let's use mathematical induction to show that, in fact, this formula is correct. Where what? Well, it follows that this is the f sub n plus 1 using this walk n. That's actually the nth term in the Fibonacci sequence, right? So let's prove that it works. Okay, here goes induction. For the basic step, n equals 1, we must show that the sum is k equals 1 to 1 of f sub k equals f sub 3 minus 1. Well, let's see. Is that true? Let's find out. Let's just calculate it. So the sum is of k equals 1 to 1 of k equals 1. The sum and f3 equals minus 1 equals 2 minus 1 equals 1. And this verifies the this verifies the claim. So for the inductive step, we assume the case n. That is, we assume that the sum is k equals 1 to n of f sub k is in fact equal to f sub n plus 2 minus 1. Okay? And then now we want to prove the case for n plus 1. So what you do is just write it down, right? And you find out that it's equal to, we want to prove that's f3 minus f sub n minus 3 minus 1. Now, let's see what we have here. Well, when you do add these up, notice we get the sum of k equals 1 to n of f sub k plus f sub n plus 1. Well, now we can use our induction to substitute here. We just substitute f sub n plus 2 minus 1 plus f sub n plus 1. And then we write that down. And what is that? Well, that's sort of the definition of the n plus third term of the Fibonacci sequence minus 1. And so we've proven our result. Okay, I hope this helps you with your questions in section 4.4. Thank you. Bye-bye.